everybody, and welcome to our next Shot Pharmaversity podcast. Today, we have a guest that a lot of you might actually know from previous sessions, as she has been here quite a few times now. Well, I'm talking about Mrs. Diana Löber, who is Global Product Manager for Vials at Shot Pharma. She will again give us an insight on a very interesting vial topic. So let me welcome her and let's see if she's here with us and I can say, hi, Diana.
Hi, Caro. Thanks for the introduction. So I'm happy to be here again, and I think it's already my fourth podcast already.
Oh, well, yeah, that's quite a lot actually. So it's really nice to have you here again with us. And I would say we jump directly into the topic of today. Diana, your Pharmaversity session this time is called Vials for Deep Cold Storage. Well, my first question is here, what is actually meant by deep cold storage? Is there kind of a definition or anything that makes it clear, I would say?
Yeah, so as it often actually is the case with terms which are used quite publicly, there is not a concrete definition. So often below 5 degrees Celsius is defined as cold or cold chain. Around minus 50 degrees, then there is the definition of ultra cold. But I mean, in general, what can be stated is that for these applications which are now relevant, there are two different thresholds which are really important. So one is at minus 80 degrees Celsius. And this is typically the lowest temperature used for viral vectors or mRNA vaccines. And this usually happens on dry ice. And then there is the range which is even below this minus 80 degrees Celsius. And this temperature level is needed to store cells. And usually this is realized via liquid nitrogen that can go down to even minus 196 degrees Celsius. So these are the two important thresholds, I would say.
Mm-hmm. Oh, sounds really very cold. And I mean, just hearing these temperatures, isn't this kind of a huge hurdle for supply chain and delivery to keep these cold temperatures as well?
Yeah, definitely it indeed is. Yeah. So I mean already cold chain. Yeah. So meaning storage which requires these fridge temperatures from 2 to 80 degrees Celsius, so around 5 degrees Celsius. I mean already this poses a big challenge to supply chain, especially for remote regions in the world. Yeah. I mean minus 20 degrees Celsius, minus 80 degrees Celsius, so even colder, huge challenge. Yeah. I mean especially to secure the temperature stability and therefore, of course, the stability of the drug transport during, of the drug during the transport. And I think it was actually Amgen, yeah. So for their oncolytic vial therapy, which is called Imlygic, they even developed a dedicated own shipping box, yeah, to ensure this temperature stability over supply chain. I mean, and in general, before COVID, there hasn't been a lot of experience with supply chain on big scale for this very cold temperature. And as far as I know, there have not been many companies which were specialized on transport in these temperature ranges. And Comirnaty, so COVID vaccine from Pfizer and BioNTech, I mean, they started with the need to be stored at minus 80 degrees Celsius. And yeah, in my opinion, a huge success isn't even enough to describe the achievement, what they actually did, yeah, of setting the supply chain up in a few months, yeah, during the pandemic here.
Definitely, yes. Yeah, not a quite easy way, I guess, and it was really an achievement that they did. But would you say, I mean, if it is so complicated and really kind of a hurdle to keep these cold temperatures, aren't there any other options apart from deep freezing? Do you see any other option?
Yeah, I mean, so what we've seen for Comirnaty, as well as for others, is of course to prove stability also in higher temperatures. Yeah, so I think today Comirnaty only requires minus 20 degrees instead of minus 80 degrees, what of course makes life already a lot easier. But nevertheless, also this temperature is still a challenge, of course. Yeah. I also heard of first attempts to freeze fry these kind of drugs, but so far I'm not aware of any promising outcome, to be honest. What I assume and what I think is, I mean, now a platform and also a belief in these therapies has been established, and yeah, more will follow for sure. So in my opinion, we will continue to have to deal with deep cold storage in the upcoming future.
Okay, understood. Well, you mentioned earlier some of the examples that need deep cold storage. I mean, the viral vectors, the cells, and mRNA vaccines. Why do specifically these therapies need this cold temperature? Is there a clear or particular reason for that?
Yeah, so I mean, one topic is, of course, yeah, the sensitivity. So as far as I understood, for mRNA and DNA vaccines, yeah, there's quite a big likelihood that in the future they can be stabilized in this way, that they can be stored at fridge temperature for quite a longer period. Yeah, but for viral vectors and cells, the outlook is a bit different, I suppose. So as living organisms, cells tend to mutate if not every biological activity is somehow suppressed, is somehow stopped. And this usually can be achieved by freezing it down to very cold temperatures. And depending from the cell, a typically required temperature is between minus 150 and minus 180 degrees Celsius. For viruses, which are somehow in the middle of living and non-living, less is actually enough, and therefore at lowest minus 80 degrees Celsius is usually necessary, yeah, to keep them from mutating.
Okay. Mhm. And well, I mean, what I'm questioning myself a bit is why are you actually having kind of a dedicated session with a focus on vials for deep cold storage? I mean, isn't it just cooling it down, thaw it, and then done? Or I don't know, isn't it like that?
Yeah, it would be nice if it was as easy as this, to be honest. Yeah, but I mean, with these freezing procedures, totally new mechanisms occur that can have an impact on different topics that might be a threat for the drug. And maybe to specify even further, different kinds of executions of the procedure can also already have a totally different impact on the drug container system. Yeah. So in focus is, of course, the design of the freezing procedure. So meaning the freezing rate, the storage temperature, the thawing rate, etc. Yeah, and of course, it needs to be done in this way that is the most beneficial, or let's say the other way around, the less harmful for the drug. But however this procedure is defined, I mean, first we have water-based solutions that expand when they are being frozen. And this can, of course, have an impact on the strength of the vial. Second, I mean, the state of the drug changes from liquid to solid, and this might also have a mechanic impact. And third, of course, you have different parts of the container closure system, which might behave differently. So the stopper compared to the glass, compared to the closure. And last but not least, I mean, there's also a potentially changed chemical interaction, yeah, that should not be forgotten. And yeah, in our test, we put a focus on CCI and on breakage.
Okay, then I mean, let's focus on the first, challenge or focus here is the CCI, as you called it. Why is this an issue? Can you elaborate this a bit more?
Yeah, so I mean, the things at common temperatures, the system of the vial, the rubber stopper, and the crimp works just fine. Yeah? But these materials, they change their behavior at these very cold temperatures. So one thing is the different shrinkage rate of the different components. Yeah, so the glass vials behavior is actually negligible, but the stopper shrinks. In addition, due to the glass transition temperature of elastomers, the stoppers goes from a flexible to a brittle state, and at certain temperatures, depending from the used material composition. And these behaviors lead to the situation that the crimp might not be able to hold the container closure integrity because it might not be able to compensate, yeah, for the gap between a brittle shrunk stopper and a vial that actually almost didn't change. And yeah, this is why we performed the test at minus 80 degrees Celsius.
Okay, and how did you show that CCI is stable then?
Yeah, so within the test matrix, we included different vial formats, different blowbacks, different stoppers. And we worked together with Genesis packaging technologies who actually took care of the controlled closing of the vials. We defined a certain compression force as well as a certain residual seal force for the different two stopper sizes that have been included. And within this definition, we also made sure that we are rather on the lower end than in the optimum case, to cover also this. And then, Genesis kind of handed over to Lighthouse, and Lighthouse then performed their well-established and well-known carbon dioxide headspace analysis in order to control if any leak occurred during storage at minus 80 degrees Celsius. And these results I've shown in the Pharma sessions. And for these ones who missed the session, it is also available on demand.
Yeah, and Diana has a point here. That is true. So just also from my end, I can say we have the Pharmaversity recording available for those who are interested in it. And thanks, Diana, for the explanation here on the CCI part. If we're coming to the second challenge that you mentioned, which was the breakage, I mean, what's the background here? Can you give our audience also a bit of a background for this one?
Yes, for sure. So, I mean, in general, glass is thermally stable, meaning that when you have a sheer perfect glass, it is stable at minus 20 degrees Celsius, at minus 80 degrees Celsius, at minus 200 degrees Celsius, and even further down. But geometry and flaws have an impact on the glass strengths. And that is a general premise, no matter which temperature we are talking about. And the thing is that with freeze-thaw cycles, this might even play a bigger role. In addition, you for sure have the stress, of course, from the expanding frozen liquid that then has puts a pressure on the inside of the vial. So these are actually the important factors here.
Okay, and what would you say, or what would you say your customers, or tell your customers that they need to consider to tackle that kind of challenge? Is there, I don't know, a way, an option that you would see that there to not recommend, but maybe what would you tell them?
Yeah, so there are definitely options. So based on our experience so far, there are a few things that have an impact and that can be influenced. But of course, these are things that need to be considered at a very early stage. So one for sure is the filling height, so filling volume in the end. So we highly recommend to never exceed nominal fill volume. Rather go with 50% of nominal fill volume or even below if possible. And this already has a huge leverage. We also have seen positive effects with slow freezing. But this is, of course, something that cannot be realized in every case because, of course, the stability of the truck is in the focus and maybe not so much the truck container stability here. What also has a very high impact is the handling of the vial. So make sure that you introduce as less defects on the outer surface as possible. Make sure that you have a gentle, smooth handling of the vials. And then, of course, the drug containment solution can have a huge impact. I mean, that's our core competence. And this is why we include different vial options in our test.
Okay, well, I mean, you just mentioned the core competency. So if I would ask you that, and maybe that brings me to my last question as well for this podcast today. So what is now SCHOTT Pharma's solution with regard to the right vial? What would you say here?
Yeah, so I mean, in general, we also can influence these two factors I just mentioned. So the quality of the outer surface and the geometry. And this is why we included our special options, so Everick Strong and Everick Freeze in our tests. And these vials, they have an improved geometry. And we could show that this in particular is beneficial for deep freezing. But to be honest, I do not want to disclose any more details here. And if you want to find out more, you have to listen to our recording, I suggest.
And that's a very good point. And well, Diana, I think giving this hint about the recording brings us also now to the real end of our podcast today. And if the audience and if you out there are interested in getting more information on this topic, feel free to check out the session. And well, to you, Diana, I can only say you have given our audience again a super interesting insight into a viral topic, which is gaining more and more importance. So let me say thank you to you for being here again and for giving us again a really good and nice introduction of a very important topic here.
Thanks, Caro. It was nice to be here.
Great. And yeah, to everybody who is listening, I would like to also thank you for your attention. Feel free to join also our upcoming Pharmaversity live sessions or enjoy listening to other podcasts that are available. And having said that, I can only say now thank you and goodbye.